The topic of this presentation is the model of the communication process at deep physical layer. And to be honest, my original idea on this second presentation was different. But I attended the lecture of Sergey, very interesting, really wonderful lecture. And Sergey touched a lot of very interesting topics. And this is one of his slides. I hope that no, it's okay for him that I show just the slide, because in this slide there are a lot of very interesting concepts that have some connections on the presentation that I'll show you. In particular, Sergey talked about the possibility of transmission at millimeter terahertz frequency in general, at very, very high frequency. And at this frequency, nanotechnology becomes a key technology. And let us come back a bit and let us analyze the communication process in a broad view. And of course, we have seen an incredible increase in the velocity of the communication from 1G, 2G, 3G. Now we are at 5G, but we are thinking about 6G. And of course, we have an increase of data rate. And the question is how fast we can run. What is the limit of the communication rate that we can reach? And well, there are some great expectations also on 5G, on some technologies, MIMO, and so on. But when we apply this theoretical concept in the real world, sometimes things are not so exciting. And the real world gives us some surprising that are not always nice. Why this? And this is the structure of the communication flow. This is called the OSI model, and we can see that at this level we have the final user, and the communication flow goes from the user down to this OSI model until this level. This is called the physical level. And at this level, we do not consider data packets on something like this. We consider bits. And this is the lowest level in a communication system. Now, let us come back a bit and let us consider an old communication system, the horse and the horseman. In this communication system, the horseman brings the information. Of course, the goal of the horseman is to be sure that information arrive at the right, let us say, place. And we have the horseman and the horse, sorry, and the goal of the horse is to bring the horseman. In the ancient time, well, the importance of the horseman was clear, but it was also clear the importance of the horse. If we do not, let us say, have a good horse, we cannot bring information. Now, in modern communication systems, the horseman is all these, let us say, stuck from the data to the bits. And the horse is the electromagnetic field, or in a larger view, let us say, the physical process that we use for communication. And usually the analysis stops at this level. Instead, in some way, the final limitations of any communication system is given by the horse. In some way, if the horse does not move, communication system does not work. Or in other words, no mathematical trick can substitute the physical level in some way. And so the idea is to add another layer under the physical layer that I call the deep physical layer. While the physical layer regards bits, the deep physical layer regards fields, or in a more general view, the physical quantity that we use to bring information. In the wireless communications, we use fields, and the quantities on which we are interested are field radiation, field propagation, and everything is let us say, ruled by first principles. This means that what we obtain at this level in some way is something that is related to the basic rules of physics, and so they are unbreakable. We cannot do things better than the equation of physics tell us. And of course, in our case, we use Maxwell equation, and this is Maxwell. But in some way, we are also interested in not only in the field, but the relationship between the field and information that can be associated to the field. So we needed the help of another giant of mathematics that is, of course, Shannon. The problem is that Shannon is based on a probability theory. Maxwell is, of course, a physical theory. We need something that allows, let us say, Shannon to talk to Maxwell. And we need someone that is as great, as, let us say, as important than Maxwell and Shannon. And the man, the researcher that we let us say we help us is Kolmogorov. Kolmogorov, well, one of the greatest mathematicians in the history, worked on a lot of things. It's very famous for probability, of course, probability theory, but among his huge body of works, there is also there are a couple of works on information theory, and he developed a special information theory that is that introduced the concept of epsilon entropy and epsilon capacity, and works in functional sets. And this theory represents the trade union between physics and mathematics in some way. And just to give an idea of the basic concepts, let us suppose that we have an electromagnetic source, and here we have currents or current density. In some way, this is our antenna. And we observe the field radiated by this antenna on an observation curve or observation surface. It's the same. The field on this observation curve is related to the currents by this linear operator. Of course, it seems simple, but it's not simple. This is the field, this is the current density, and this is the Green function. And all the complexity is inside the Green function. But let us suppose that we are able to write this integral, and we know the green function for a lot of cases. And let us expand the currents and the field in series. These Fk and Gk are the basis, and Xk and Yk are the coefficients. And of course, these coefficients, x1, x2, x3, and so on, can be represented by a point in a functional space, as well as the coefficients epsilon1, epsilon2, epsilon3, and so on, that identify a point in another functional space. The first space collects all the possible currents on the antenna. The second functional space collects all the possible distribution of field on the observation domain. We have, of course, this linear operator. We can diagonalize this operator using the Hilbert-Schmidt decomposition, and we can relate each component of y to the component of x through this number. This is called the singular value of the operator. This operation is basically, as I told you, a diagonalization of the integral operator. And what is interesting in our case is that these coefficients, even if they are infinite, they goes to zero. And so this means that the operator has a rank that is almost finite. And the essential dimension of this operator is called the number of degrees of freedom of the field. And so the transmission process at the deep physical layer is the following one. Let us consider the physical layer. In this physical layer, we have bits. For example, let us consider that we have the sequence 0, 0. We associate this sequence to a specific current distribution on the antenna. This current distribution is represented in the set X, that is the set of all the possible currents on the antenna, by a point in this functional space. The radiation operator is basically maps this point in a point that belongs to the space Y. The space Y is the space of all the possible fields on the observation domain. And this point is, for example, associated to this field configuration. We observe this field configuration, and then we associate to this field configuration the sequence 0, 0. So this is the physical process that allows to transmit the bit 0, 0 from the transmitter to the receiver. Of course, if I have another sequence, for example, 0, 1, I associate this sequence to a different current distribution, so a different point in this functional space X. The radiation operator, so when this current is radiated, we have this point in the set Y that is associated to this field observed on the observation domain, and then we can reconstruct 0, 1, and so on. This is the process of the transmission of bits at the deep physical layer. What I want to stress now is that when we go from physical layer to deep physical layer, all this part is just, let us say, the mathematics of a physical quantity. So we are working on electromagnetic field. We can work also on a different physical quantity. So the important thing is that we are able to represent the transmission process in terms of operator. And so there is a small problem that is not so little. If we use currents such that we have current field configurations that are too close, we must take into account that we have always noise at the receiver. So we have a sphere of uncertainty. When we receive this quantity, due to the noise, this point, instead of this point, we could receive a point here, 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 in this sphere of uncertainty. And if two fields are inside the same sphere of uncertainty, of course, we are not able to identify the sequence of bits. So this means that the maximum number of information that we can send is a solution of a sphere packing problem. That means how many spheres of uncertainty can we pack in the set Y? The maximum number of spheres of uncertainty that we can pack gives us the maximum number of information. And this is called the epsilon capacity of Kolmogorov. So, in practice, the Kolmogorov epsilon capacity is the maximum amount of information expressed in bits that we can transmit along this special channel. And the effective dimension of this set is called the number of degrees of freedom of the field, as I told before, and it's a very important quantity to understand the amount of information that we can send. In order to clarify this, let us consider the relationship between the coefficients of the field and the coefficients of the currents. If we evaluate the Kolmogorov epsilon capacity, what we have is that the Kolmogorov epsilon capacity is related to the logarithm of, this is the singular, the kth singular value, this is the radius of uncertainty, and what is important is this sum. This sum is from 1 to the number of degrees of freedom of the field. And of course, well, this part is important, but there is a logarithm. So we have a quite not fast, quite slow increase with this quantity inside the brackets. But this term is a sum. So this means that this term, when we increase the number of degrees of freedom, we are able to increase the capacity very, very fast, in a very, very fast way. So having more number of degrees of freedom of the field means to be able to send much more information along our communication channel. There are a lot of applications on this, but I skip the application. I want just to show this figure. When I studied this, I tried to understand what happens when I move the observation point very, very close to the source. And here you see the ratio between the degrees of freedom of the field that I have and the degrees of freedom of the field that I have at very large distance. So it gives an idea of how the degrees of freedom of the fields change when I move the observation surface from the infinite to very, very close to the surface as function of the signal-noise ratio. But what is important is d over lambda is the distance between the source, that in this case is a circular source, because in this case I'm able to evaluate the singular values in a closed way. And d is the distance between the source and the observation domain, that is this dashed curve. And when d is, for example, 1 lambda, we have that the degrees of freedom for signal noise ratio of, let us say, reasonable value 10, 20 dB are almost equal to the ones that we have when the observation curve is at infinite. But when I move the observation domain very, very, very close to the source, I see that the degrees of freedom tends to increase. This is the ratio, and I can see that the degrees of freedom tends to be larger, larger, larger. This means that when I move very, very close to the source, I have the possibility to transmit much, much more information. We have a capacity that fast increases. And this is, I think, it could be, let us say, interesting from a theoretical point of view, but, well, when I studied this, I stopped here because I was interested in communication systems, standard communication systems, whose distance is very, very large. But when I saw the presentation of Sergey, I remembered, let's say, this slide, and well, why this slide could be useful or could give some ideas for the future. First of all, this physical layer is able to describe the physical mechanism at the basis of communication process. This means that we can use different physical mechanisms, including, for example, we can arrive to the quantum level. It depends on how good we are in modeling the communication systems, or in other words, if we are able to include the mathematics in the model. But is this interesting? Is going to such a small distance could be really interesting, or it's just a theoretical thing? And what is interesting is that indeed the research, but I'm sure that we are, we know, you know this, I'm new in this field, but you are, of course, very, you know all the novelty of this field. And what I was, well, I was surprised and also interested, for example, in the fact that the research is moving very fast toward nano, for example, nano communication, nano radio. This is an example of nano radio. This is from University of California. It's something that it's interesting because I think it's one of the first example of the use of carbon nanotube for communication, wireless communication. And this is just the starting point, I think. Well, this is the starting point of for the nano networking. Nano networking or nanoscale network, this is a definition that I found, is a set of interconnected nanomachines which are able to perform very simple tasks and so on. And this is not just a pure theoretical thing. There are there is a larger research on this. For example, on IEEE access, there is a special number of protocols for nano-communication networks. There are some papers, some journals on nano-communication networks, and what surprised me is that there is a group on IEEE that is working on recommended practice for nanoscale and molecular communication frameworks. And just to show you the interest in this moment of this topic, for example, this is IEEE Communication Magazine, May 2021. So it's yesterday in some way. It's just yesterday, in which, well, this is a special issue of networking at micro scale and so on. So there is a real interest toward communication at very short distance. Of course, the natural, let us say, more natural approach is the nano networking using electromagnetic waves. This is called electromagnetic nanonetworking, in which artificial nanomachines communicate using electromagnetic radiation. And in some way, the deep physical layer gives, in this case, a natural framework from electromagnetic-based networks. But of course, there are something more. It's possible to use molecular nanonetworking. I don't know much about this. Surely wave equations does not work. We need something related to diffusion equation, but probably this is not enough. So just to conclude, well, this is the standard OSI stack, and this is what there is at the very basis level. And in this moment, we have fields for communications. We have Maxwell equations. But probably in the future, we will substitute this with something different. I don't know exactly what, maybe quantum fields, quantum theory. The future is completely open. And well, what happens in this nano-world communication, I have no idea, I admit, but I think it's something interesting. And I think that your research on nanotechnologies is a key, let us say, a key technology for the future of communication systems. So my presentation is just to give some, let us say, some suggestions, some ideas about how your research, your very interesting, very exciting research can be used in the future. Applications are, I don't know, they are huge. I have no idea what happens. But what is sure is that what Feynman told many years ago is still true, and there is plenty of room at the bottom. I conclude this presentation just to tell you that there is a video on the deep physical layer is available on YouTube. It's the video abstract of a paper that was published in IEEE Access. So if you are curious, you can see this video. Thank you very much.